something changed. Just days after 3IATLAS made its closest approach to the Sun, astronomers detected something they weren't expecting. A complex jet structure emanating from the object in multiple directions, far more intricate than the simple tail you'd typically expect from a comet. This unexpected change, along with the timing, is what makes it fascinating. Let me ask you something. When was the last time you saw a comet that behaved like this? One that accelerated without a visible cause, changed colors from red to deep blue in a matter of days, lost its tail, and then suddenly developed multiple jets pointing in different directions? If you're struggling to remember, that's because it's never happened before, at least not in any comet we've studied. Here's what we know now, and trust me, this is where things get really interesting. On October 24th, the Meerkat radio telescope in South Africa picked up something extraordinary, the first radio signal from 3IATLAS. It wasn't a transmission, but absorption lines from hydroxyl radicals, OH molecules, being released from the object. This detection came just days after the object's perihelion, its closest point to the Sun. What makes this remarkable is not just that they detected it, but what the signal tells us about what's happening on the surface of this object. The hydroxyl radicals were detected at two specific radio frequencies, 1.665 and 1.667 gigahertz. The Doppler shift of these signals revealed something crucial. The object was moving at exactly the velocity we expected. But here's the catch. Previous attempts to detect these same signals in late September had failed. Nothing. Radio silence. Then, suddenly, as 3IATLAS swung around the Sun, these molecules appeared. It was as if something activated. Before jumping to conclusions, let me explain what hydroxyl radicals are. They're fragments of water molecules, broken apart by intense solar radiation. Every comet releases them when it gets close to the Sun. This is normal and expected. But the timing here, the sudden appearance of these molecules after weeks of nothing, raises questions. Was the surface of 3IATLAS so cold and inactive during its approach that it only started releasing gases at the last possible moment? Or is there something else going on? Professor Abby Lowe, the Harvard astrophysicist who has been tracking this object from day one, noted something intriguing in his analysis. The thermal broadening of the O absorption lines matched perfectly with what you'd expect from a surface temperature of about 230 Kelvin. That's cold, very cold. But what caught his attention even more was the width of those absorption lines. The full width at half maximum, as astronomers call it, was remarkably narrow, less than 1.12 kilometers per second. This suggests that the gases weren't being violently ejected. They were seeping out almost methodically. But that's not the strangest part.
What happened after perihelion is what really has astronomers scratching their heads. The Atacama Large Millimeter Array, ALMA, one of the most powerful radio telescope networks on Earth, observed 3IATLAS and found something unexpected. The object was 4 arcseconds off its predicted trajectory. 4 arcseconds might not sound like much, but in astronomical terms, when you're tracking an object millions of kilometers away with precision instruments, that's significant. This isn't a minor measurement error. This is a real deviation. And what's more interesting, the deviation wasn't random. It was consistent with non-gravitational acceleration. Something had pushed 3IATLAS slightly off course. Now, comets experience this all the time. When ice vaporizes on the surface, it creates tiny jets of gas that act like miniature rocket engines, nudging the comet in different directions. This is called outgassing, and it's completely natural. But here's the problem. The amount of acceleration observed in 3IATLAS was unusually strong for an object that showed relatively little visible outgassing activity. Think about it. If 3IATLAS was releasing enough gas to push itself off its trajectory by this much, we should have seen a massive coma, a huge cloud of gas and dust surrounding it. We should have seen a bright, active tail. Instead, what did we see? A relatively subdued object that actually lost its tail shortly after perihelion. So where did this acceleration come from? Lowe suggested something that made headlines around the world. He didn't rule out the possibility, however remote, that the acceleration could be the result of something artificial, an internal engine or propulsion system. Now, before you dismiss this as science fiction, consider what he actually said. He didn't claim it was aliens. He said that if no massive gas cloud is observed around 3I/ATLAS in the coming weeks, then the non-gravitational acceleration might, emphasis on might, be regarded as a technological signature. That's the scientific method at work. You observe something unusual, you look for natural explanations, and if those explanations don't fit the data, you consider alternatives, even uncomfortable ones. But let's talk about what happened next, because this is where the mystery deepens even further. Images from the Hubble Space Telescope and ground-based observatories revealed something absolutely fascinating. After perihelion, 3I/ATLAS began exhibiting a complex jet structure. It wasn't a single tail streaming behind it like a typical comet. Instead, multiple jets emanated from different points on the surface, pointing in various directions. It looked less like a comet and more like something regulating its trajectory. One particularly intriguing image from the 2-meter twin telescope showed a sunward jet, an active stream of material pointing directly toward the sun. This is unusual.
Comet tails are typically pushed away from the sun by solar radiation pressure. They stream behind the comet, like hair in the wind. But a sunward jet suggests that material is being actively expelled from the night side of the object, the side facing away from the sun, with enough force to arc around and point toward the sun. Or, and here's where it gets speculative, it could indicate directional venting from specific locations on the surface. Why does this matter? Because if the outgassing were purely passive, driven only by solar heating, you'd expect it to be roughly symmetrical, concentrated on the side facing the sun. But if you're seeing jets emanating from multiple locations, including the night side, that suggests something more complex. Either the interior of 3I/ATLAS is unusually warm, maintaining heat even on the side not facing the sun, or there are specific vents, specific locations where gas is being released. And then there's the color change. We need to talk about this because it's genuinely bizarre. When 3I/ATLAS was first observed in July, it appeared reddish. This is normal for objects in space. Cosmic dust, organic compounds, and such typically give objects a reddish hue. But as it approached the sun, something changed. The object began turning blue, deep blue. By the time it reached perihelion, it was exhibiting a striking blue-green color that astronomers had rarely, if ever, seen in a comet. Now, there are natural explanations for color changes. As a comet heats up, different ices sublimate at different temperatures. Water ice, carbon monoxide ice, carbon dioxide ice, they all vaporize at different points, and each one scatters light differently. But the shift from red to blue is counterintuitive. Typically, as dust is released from a comet, it scatters light and makes the comet appear redder, not bluer. So what could cause this blue color? One possibility is that we're seeing light scattered by very small particles, smaller than typical comet dust. When particles are extremely tiny, they scatter blue light more efficiently than red light. It's the same reason the sky is blue. But if that's the case, where are these tiny particles coming from, and why did they only appear as the object approached the sun? Another possibility, and this is where things get speculative, is that we're seeing emission from specific gases, cyanogen and diatomic carbon, both of which can produce a blue-green glow when excited by sunlight. But again, the question is, why now? Why did these gases suddenly appear in such quantities during and after perihelion? NASA released a statement attempting to calm public concern. Acting Administrator Sean Duffy responded to questions, including one from Kim Kardashian. Yes, that Kim Kardashian, assuring everyone that 3I/ATLAS is simply the third interstellar comet to pass through our solar system. No aliens, no threat, just a comet doing comet things.
But here's the thing. Not everyone is convinced that we're getting the full picture. Renowned physicist Dr. Brian Cox publicly criticized NASA for what he called unnecessary secrecy surrounding 3I/ATLAS. In a strongly worded statement, Cox argued that the space agency had been withholding crucial images and data from the public, particularly high-resolution images captured by the Mars Reconnaissance Orbiter on October 2nd and 3rd, when 3I/ATLAS passed within approximately 30 million kilometers of Mars. Cox's criticism didn't stop there. He pointed to specific data that, in his view, raised serious questions about the nature of 3I-ATLAS. The object's estimated age, approximately 7 billion years, was significantly older than our entire solar system. Its unusually high nickel content suggested it was composed of materials far older and tougher than anything originating from our cosmic neighborhood. And most provocatively, he noted that while an extraterrestrial origin for 3I-ATLAS remains highly unlikely, respected scientists like Harvard's Avi Loeb haven't ruled it out completely. The physicist's main concern wasn't about aliens. It was about transparency. In Cox's words, unnecessary secrecy only fuels conspiracy theories. When the public can't access data, when images are delayed or withheld, people start asking why. What is there to hide? If 3I-ATLAS is just a comet, why not release all the data and settle the matter? And that question, the simple why, has now reached the halls of Congress. Florida Congresswoman Anna Paulina Luna formally requested that NASA release all observational data related to 3I-ATLAS, specifically the images captured by the Mars Reconnaissance Orbiter's high-rise camera between October 2nd and 3rd. In her letter, Luna emphasized that this information is crucial to advancing our understanding of interstellar visitors and their interaction with our solar system. But she didn't stop at Mars data. Luna also requested supplementary data from the Mars Orbiter, the Perseverance rover, and other Mars missions that may have detected unusual activity near Mars around or after October 3rd, when 3I-ATLAS made its closest approach to the red planet. Why Mars? Because that close pass offered a unique opportunity. Mars-based instruments could potentially observe 3I-ATLAS from a different angle, providing data that Earth-based telescopes couldn't capture. If there was anything unusual about the object's trajectory, surface activity, or composition, the Mars missions would have been perfectly positioned to detect it. The fact that this data hasn't been publicly released weeks after the encounter has raised eyebrows. Is NASA being cautious, carefully analyzing the data before making it public? Or is there something in those images that requires a more delicate approach? We don't have those answers yet.
What we do have is a growing list of anomalies, a growing list of behaviors that don't quite fit the profile of a normal comet, and a growing chorus of voices, from scientists to public figures to elected officials, demanding more transparency. So, where does this leave us? What do we actually know about 3I-ATLAS right now? We know it's real. We know it came from interstellar space. We know it's heading toward its closest approach to Earth in late December. We know it exhibited unusual behaviors during perihelion, including non-gravitational acceleration, a dramatic color change, the loss of its original tail, and the development of complex jet structures. We know it released hydroxyl radicals in a pattern that suggests sudden activation rather than gradual warming. And we know that some of the world's leading physicists and astronomers are puzzled by what they're seeing. What we don't know is what happens next, and that's what makes this so compelling. In just a few weeks, 3I-ATLAS will pass close enough to Earth that amateur astronomers with decent telescopes will be able to observe it directly. No need to rely solely on NASA, ESA, or any space agency. Thousands of independent observers will have their instruments pointed at this object. And if there's something unusual happening, something that doesn't match the official narrative, we'll know. That's the beautiful thing about astronomy. It's one of the few sciences where amateurs can contribute meaningful observations, where transparency isn't optional, it's inevitable. The sky belongs to everyone. But until then, we're left with questions, tantalizing questions. Is 3I-ATLAS simply an unusually active comet from another star system? Or is there something more going on? Something we haven't considered? Something that challenges our understanding of what's possible? There's something about the timing that keeps nagging at researchers, something that doesn't quite add up. Let me walk you through it, because once you see the pattern, you can't unsee it. 3IATLAS remained relatively quiet during its entire approach to the Sun. Months of observations showed a standard, if somewhat dim, interstellar comet, nothing particularly remarkable. Then, in the span of just a few days around perihelion, everything changed. The radio signals appeared, the jets activated, the color shifted, the trajectory deviated. It's almost as if the object knew exactly when to turn on. Now, I know what you're thinking. Comets do become more active as they approach the Sun. That's basic solar system physics. The closer you get to a heat source, the more ice you sublimate, the more active you become. It's gradual, predictable, and well understood. Except 3IATLAS didn't follow that gradual pattern. It was relatively dormant, and then suddenly, right at perihelion, it lit up, like a switch had been flipped. Dr. Abilow pointed out something fascinating in his recent analysis.
The Meerkat telescope tried to detect those hydroxyl radical signals twice before they succeeded, once on September 20th and again on September 28th. Both attempts came up empty. No signal, no absorption lines, nothing. Then on October 24th, 5 days before perihelion, there it was. Clear and unmistakable, exactly where they were looking. So what changed? Did the surface of 3IATLAS suddenly warm up enough to release water molecules in those 5 days? Possibly. But that would require an enormous temperature shift in a very short period. Or, and this is the question that's bothering some researchers, was there a delay mechanism? Something that kept the surface inactive until a specific point in the object's trajectory? Before you jump to conclusions, let me be clear. There are natural explanations for delayed outgassing. Some comets have thick, insulating crusts that prevent gases from escaping until the internal pressure builds up enough to crack through. It's like a pressure cooker. Heat builds, pressure builds, and then suddenly, boom, everything releases at once. It's possible that's what happened here. But here's what makes this scenario interesting. If 3IATLAS has been traveling through interstellar space for potentially billions of years, experiencing temperatures just a few degrees above absolute zero, any surface ice should be pristine, pure, without the kind of dust and debris that would form an insulating crust. Objects that cold don't accumulate the kind of material that would block outgassing. They're essentially clean ice balls, frozen in time, unless, of course, the surface isn't made of ice at all, or at least not primarily ice. That brings us to something Cox mentioned that caught a lot of attention, the unusually high nickel content. Now, I want to be careful here because we don't have direct spectroscopic analysis of 3IATLAS's surface composition. What we have are preliminary assessments based on the object's reflectivity, its color, and comparisons to known materials. But if the nickel content is indeed higher than expected, that would be significant. Why? Because nickel is typically found in the cores of differentiated objects, planets, large asteroids, bodies that were once hot enough for heavy elements to sink to the center while lighter materials floated to the surface. You don't usually find high nickel concentrations in comets, which are supposed to be primordial, undifferentiated chunks of ice and rock that never got hot enough to separate into layers. So if 3IATLAS shows high nickel content, it suggests one of two things. Either it's a fragment of a destroyed planet from another star system, a chunk of core material that got blasted into interstellar space billions of years ago, or, and this is where things get uncomfortable for some scientists, it's made of something that isn't natural, something manufactured. I know how that sounds. I know it's a leap.
But let's think about it logically. If you were going to send a probe on an interstellar journey lasting potentially millions or billions of years, what would you make it out of? You'd want something durable, something that could withstand cosmic radiation, micrometeorite impacts, and the extreme cold of interstellar space. You'd want metals. Nickel-iron alloys are some of the most durable materials known. They don't degrade. They don't break down. they last. Am I saying 3IATLAS is a probe? No. I'm saying that if we're going to be scientifically rigorous, we need to consider all possibilities that fit the observed data. And right now, the data is showing us something that doesn't perfectly fit the comet model. Let's talk about the trajectory deviation again, because there's more to this story. The Atacama Large Millimeter Array, ALMA, observed 3IATLAS and found it 4 arcseconds off its predicted position. Now, in his analysis, Loeb calculated what kind of outgassing would be required to produce that deviation. The numbers are interesting. To push an object the size of 3IATLAS that far off course would require a significant release of gas. We're talking about tons of material being ejected at high velocity. But here's the problem. When you release that much gas, you create a visible coma, a large bright cloud of material surrounding the nucleus. It's unavoidable. The gas expands, carries dust with it, scatters sunlight, and becomes easily observable from Earth. Every major comet outburst in history has been accompanied by a dramatic brightening and expansion of the coma. You can't hide it. So where's the coma? Images from the Hubble Space Telescope and ground-based observatories show a relatively compact object. Yes, there's some material around it. Yes, there are those jets we talked about, but nothing on the scale you'd expect from an outgassing event powerful enough to alter the trajectory by 4 arcseconds. This is what Loeb was getting at when he suggested the possibility of a propulsion system. If the acceleration isn't coming from visible outgassing, where is it coming from? There has to be a mechanism. Something is pushing this object. The laws of physics don't just break down because we're dealing with an interstellar visitor. One possibility that's been suggested is subsurface venting. Instead of gases escaping uniformly from the sunlit surface, they might be channeling through internal fractures and venting from specific locations. This could produce thrust without creating a massive visible coma. It's an elegant solution, and it's certainly possible, but it would require a very specific internal structure, a network of channels or vents that just happen to be oriented in a way that produces measurable acceleration. How likely is that for a natural object? Well, that's the question. Now let's talk about something that happened recently that hasn't gotten nearly enough attention.
The appearance of what Loeb described as a complex jet structure. This isn't your typical comet tail. This is something different. Images from multiple observatories have shown 3IATLAS exhibiting jets emanating from various locations across its surface. Some pointing away from the sun, which is normal, but some pointing in other directions, sideways, even toward the sun. This creates an appearance that some have described as almost geometric, structured, not random. One of the most detailed images came from the 2-meter twin telescope, which captured what appears to be a sunward jet. This is the jet pointing toward the sun, which, as I mentioned earlier, is unusual. Comet tails are blown away from the sun by solar wind and radiation pressure. They stream behind the comet like flags in a breeze, always away from the sun, always. But a sunward jet suggests active venting from the night side of the object, with enough force to overcome solar radiation pressure. Or it suggests material being expelled in a direction that has nothing to do with passive solar heating. Either way, it indicates processes we don't fully understand. What's particularly intriguing is that the jet structure appeared after perihelion, not during the approach. Most comets are most active during their approach to the sun and at perihelion. As they move away, they cool down, the activity decreases, and they gradually return to dormancy. But 3IATLAS seems to have increased its activity after its closest approach. That's backwards from what we normally see. Unless, of course, perihelion wasn't just a gravitational event, unless it was a trigger. I want to pause here and address something important. Throughout this entire discussion, I've been presenting hypotheticals and questions. That's deliberate, because right now we're in a phase of this story where we have more questions than answers.
And that's okay. That's actually how science is supposed to work. The problem arises when we stop asking questions, when we settle on an explanation prematurely because it's comfortable or familiar, when we dismiss anomalies because they don't fit our current models. That's not science. That's dogma. And right now, there's a tension in the scientific community between those who want to carefully study every aspect of 3IATLAS with an open mind, and those who've already decided it's just a comet, and any suggestion otherwise is sensationalism. This tension came to a head in a recent interview between Avi Lowe and a British journalist on LBC. The interviewer pressed Lowe on whether he was being irresponsible by not immediately dismissing the possibility of artificial origin. The assumption was that a responsible scientist would say, "It's definitely just a comet. Nothing to see here. Move along." But Lowe pushed back. He argued that the truly irresponsible thing would be to make conclusions before all the data is in, to assume we know what something is before we fully studied it, to let our biases about what we expect to find cloud our analysis of what we're actually observing. And you know what? He's right. Think about it this way. Imagine if astronomers in the 19th century had observed radio signals from space. They would have had no framework for understanding them, no knowledge of pulsars or quasars or any natural source of radio waves. If they had been rigidly dogmatic, they might have dismissed the observations as instrument errors or interference. They might have refused to publish the data because it didn't fit their understanding of the universe. But the good ones, the truly great scientists of that era, would have documented the observations carefully, published the data, and admitted they didn't know what they were seeing. They would have let future scientists with better tools and better understanding figure it out. That's the position we're in now with 3IATLAS. We're seeing things that don't perfectly match our models. We have anomalies, we have questions. And the appropriate response isn't to force-fit everything into the comet model and call it a day. The appropriate response is to keep observing, keep analyzing, and remain open to wherever the data leads us, even if it leads somewhere unexpected. Here's something else that's been bothering researchers. The age estimate, 7 billion years. Now, where does that number come from? It's not like we can carbon date an object in space. The estimate is based on the object's trajectory and speed, traced backward through the galaxy. When you calculate where 3IATLAS came from based on its current velocity and direction, you end up with a region of space where stars formed approximately 7 billion years ago, much older than our Sun, which is only 4.6 billion years old. This suggests that 3IATLAS originated in an ancient star system, one that formed when the universe was half its current age. Why does that matter? Because objects that old have had a very long time to be shaped by their environment, a very long time to be modified, a very long time to potentially encounter things we can't imagine. If 3IATLAS is indeed 7 billion years old, it's been traveling through interstellar space for longer than complex life has existed on Earth. That's a journey we can barely comprehend. What happens to an object over that timescale? Does it remain pristine, untouched by the eons? Or does it change? Does it accumulate material? Does it interact with interstellar clouds? Does it pass through regions of space we know nothing about? We don't know. We've never tracked anything over that kind of time frame. Every comet we've studied in detail has been a resident of our solar system, billions of years younger, with a known history. 3IATLAS is different. It's a visitor from deep time, and that alone makes it worthy of extraordinary scrutiny. But there's something else.
Something that happened recently that hasn't gotten nearly enough attention, and it involves a signal that some researchers are calling eerily familiar. The hydroxyl radical absorption detected by MeerKAT was at frequencies of 1.665 and 1.667 gigahertz. Now, those frequencies are significant in astronomy because they're in the same general range as the famous WOW signal detected in 1977. The WOW signal came in at 1.42 gigahertz. Not exactly the same, but close enough to raise eyebrows. But here's what's really interesting. When Avi Loeb analyzed the arrival direction of 3IATLAS, he found that it came from a region of space within 9 degrees of where the WOW signal originated. 9 degrees! That's less than 20 times the width of the full moon in the sky. Is that a coincidence? Probably. Space is big, and 9 degrees is a fairly large angular separation in astronomical terms. But it's the kind of coincidence that makes you pause, that makes you think, especially when you combine it with everything else we've been discussing. The WOW signal remains one of the greatest mysteries in the search for extraterrestrial intelligence. It was a strong, narrowband radio signal that lasted 72 seconds and has never been detected again. It was so unusual that the astronomer who first saw it on the printout wrote "Wow" in the margin, and the name stuck. For decades, scientists have tried to find a natural explanation for the WOW signal. Some have suggested it was interference from a passing satellite, though the signal's characteristics don't match that explanation. Others have proposed a comet releasing hydrogen clouds. Those subsequent observations of the proposed comets found nothing. The signal remains unexplained. And now we have 3IATLAS, originating from nearly the same region of space, exhibiting unusual behaviors and emitting detectable radio signatures. Am I saying they're connected? No. But am I saying it's interesting enough to warrant investigation? Absolutely. This is exactly the kind of data that should be made public. This is exactly why transparency matters. Because when you have multiple anomalies potentially pointing in the same direction, you need the broader scientific community involved. You need independent verification. You need different perspectives and different expertise examining the same data. Which brings us back to the current controversy: the missing images, the delayed data releases, and the growing frustration among researchers and the public. Congresswoman Anna Paulina Luna's letter to NASA wasn't just a polite request. It was a formal demand for specific data that, according to her office, should have been made public weeks ago. The high-rise camera on the Mars Reconnaissance Orbiter captured images of 3IATLAS on October 2nd and 3rd. High-resolution images, the kind of detail that could potentially show surface features, jet activity, maybe even structural characteristics. Where are those images?
NASA's official position is that all data goes through standard review processes before public release: quality checks, calibration, analysis. That's normal procedure, and it usually takes time. But here's the thing. When the Mars Reconnaissance Orbiter captured images of other comets, other asteroids, other objects of interest, those images were released within days, sometimes within hours. The standard review process didn't take weeks. So why is 3IATLAS different? Dr. Brian Cox didn't mince words when he addressed this question. He stated flatly that there's no legitimate reason for the delay. In his view, and he's not alone, the images should be declassified immediately. This isn't military intelligence. This isn't sensitive national security data. This is an astronomical observation of a natural, or possibly natural, object passing through our solar system. The default should be transparency, not secrecy. His concern, and it's a valid one, is that delays breed suspicion. When the public sees the data is being withheld, they start asking why. And in the absence of official explanations, they fill in the blanks themselves. Some of those explanations are measured and reasonable, others are wild and conspiratorial. But all of them stem from the same root cause: a lack of information. If NASA has the images and they show a boring normal comet doing boring normal comet things, then release them. Problem solved. Speculation ends, everyone moves on. But if the images show something unusual, something that requires careful analysis and consideration before making it public, then we're in different territory. Then the delay makes sense, but it also confirms that there's something worth being careful about. Either way, the silence is becoming untenable. Cox pointed out something else that's been largely overlooked in the mainstream coverage. The Perseverance rover and other Mars missions were operational during 3IATLAS's closest approach to Mars. They have instruments, cameras, spectrometers. If anything unusual happened, if there was any detectable activity, those missions would have recorded it. Luna's letter specifically requested supplementary data from Perseverance and other Mars missions that may have detected unusual activity near Mars around or after October 3rd, when 3IATLAS made its closest approach to the red planet. That phrasing is interesting. Unusual activity. Not just observations of the comet, but unusual activity. What kind of activity are we talking about? We don't know because the data hasn't been released. But the fact that a member of Congress felt it necessary to formally request it suggests that there are questions being asked behind closed doors, questions that the public isn't privy to yet. Let me be clear about something. I'm not suggesting there's a massive conspiracy to hide evidence of alien spacecraft. That's not what this is about.
What this is about is the fundamental principle of scientific transparency. When public institutions funded by taxpayer money make observations of objects in our solar system, that data belongs to everyone. It should be shared. It should be scrutinized by independent researchers. It should be debated, analyzed, and discussed openly. That's how science works. That's how we make progress. Not through secrecy and delayed releases and carefully managed messaging, but through open collaboration and peer review. And right now, we're not getting that. Here's something that happened just recently that adds another layer to this story. Reports emerged that 3IATLAS has been experiencing what some researchers are calling velocity shifts. Not just the single acceleration detected near perihelion, but ongoing changes in speed that don't align perfectly with gravitational models. Now, before we go further, let me explain what this means. When you track an object in space, you can predict its future position based on its current velocity and the gravitational influences acting on it. The sun pulls on it, the planets pull on it, though much more weakly. You add up all those forces, run the calculations, and you get a predicted trajectory. For 3IATLAS, those predictions have had to be updated multiple times. Each time astronomers get new observations, they find the object isn't quite where the model said it should be. Small deviations, yes, but consistent ones. And the adjustments required to match the observations suggest that something is affecting its velocity beyond simple gravity. Outgassing is the obvious culprit. As I've mentioned, when comets release gas, it can push them slightly off course. But here's the interesting part. The velocity changes don't seem to correlate perfectly with visible outgassing activity. There have been periods where the object appeared relatively quiet, yet the trajectory still required correction. And there have been periods of apparent activity where the trajectory stayed closer to predictions. It's almost as if the outgassing, if that's what it is coming in bursts, timed bursts, not the continuous, gradually changing activity you'd expect from passive solar heating. Avi Lowe has been monitoring this closely, and in one of his recent posts, he suggested something that made headlines around the world. If 3IATLAS continues to show trajectory modifications without corresponding visual evidence of massive gas release, he wrote, we might need to consider the possibility that we're observing controlled adjustments. Controlled, that's the word that got people's attention, because controlled implies intention. It implies purpose. It implies something making decisions about where to go. Now, Lowe was careful to frame this as a possibility to be tested, not a conclusion. He outlined what observations would be needed to confirm or refute this hypothesis.
Specifically, detailed monitoring of the object's velocity over the coming weeks, combined with simultaneous observations of any gas or dust emission. If the velocity changes without visible emissions, that's significant. If emissions occur without velocity changes, that's also significant. Either result tells us something important about what's happening. But to do that analysis, to really nail down what's going on, we need data. We need those Mars images. We need spectroscopic observations from multiple wavelengths. We need radio telescope monitoring. We need everything we can get. And some of that data is sitting in NASA's servers unreleased. Let's talk about what's going to happen next, because this is where things get really interesting. 3IATLAS is currently on a trajectory that will bring it to its closest approach to Earth on December 19th. That's about 5 weeks away. At its closest, it will pass within approximately 93 million kilometers of our planet. That's about 60% of Earth's distance from the Sun. Not particularly close by astronomical standards, but close enough. Close enough for what? Close enough for detailed observation by professional and amateur astronomers worldwide. Close enough for spectroscopic analysis that could reveal its composition. Close enough for radar observations that might show surface features. Close enough to potentially settle some of these questions once and for all. But here's the thing. That December 19th flyby isn't just a passive observation opportunity. It's a test of everything we think we know about this object. If 3IATLAS is simply a comet, its behavior during its Earth approach should be predictable. It might brighten slightly due to increased solar heating as it swings through the inner solar system. It might develop more visible tail activity, but fundamentally it should behave like comets behave. Passive, predictable, following the laws of physics, and nothing more. But if 3IATLAS is something else, if there's any truth to the more exotic hypotheses being discussed, then the Earth flyby might trigger something. A change in trajectory, a change in activity, something that reveals its true nature. Am I saying we should expect alien spacecraft to decloak and make contact? No, that's absurd. But am I saying we should pay very close attention to any anomalies during that flyby? Absolutely. Because anomalies are how we learn. Anomalies are how we discover new physics, new chemistry, new phenomena we didn't know existed. And 3IATLAS has given us plenty of anomalies already. There's another aspect to this that hasn't been discussed much, but it's worth considering. The psychological impact, the cultural impact. For the first time in human history, we're watching an object from another star system pass through our cosmic neighborhood in real time.
Not something we discovered after the fact like Oumuamua, which was detected on its way out, but something we're tracking from approach to perihelion to departure. And it's behaving strangely enough that serious scientists are publicly discussing the possibility, however remote, that it might not be entirely natural. Think about what that means. Think about how that changes the conversation. For decades, the search for extraterrestrial intelligence has been largely theoretical. We've been sending radio signals into space, listening for replies that never come, searching for technosignatures in distant star systems. It's been an exercise in patience, statistics, and hope. But 3IATLAS has brought that search into our backyard. Suddenly, it's not about signals from hundreds of light years away. It's about something right here, right now, passing through our solar system. Something we can observe directly, something we can potentially interact with. Even if it turns out to be completely natural, even if every anomaly has a mundane explanation, the fact that we're having this conversation at all is significant. It means we're taking the possibility of contact seriously. It means we're asking the right questions. It means we're prepared intellectually and scientifically to handle whatever answers we find. And that's progress, real progress. But let's bring this back to Earth. Literally. What can you, as someone interested in this story, actually do? What role can the public play in unraveling this mystery? First, if you have access to a telescope, point it at 3IATLAS. Observations from amateur astronomers have contributed enormously to our understanding of comets over the years. You don't need a research-grade instrument. A decent backyard telescope with a camera can capture useful data, especially if you're consistent and document everything carefully. Second, stay skeptical but open-minded. There's a lot of noise surrounding this story, a lot of sensationalized headlines and wild speculation. But there's also legitimate scientific inquiry happening. Learn to distinguish between the two. Look for primary sources. Read the actual research papers and observation reports, not just the summaries. Third, demand transparency. not aggressively or confrontationally, but persistently. Write to your representatives, write to NASA, write to the scientific journals. Let them know that the public is paying attention and expects to be kept informed. Transparency isn't just good ethics, it's good science. And fourth, remember that uncertainty is okay. We don't have to have all the answers right now. We don't have to force conclusions before the data is complete. It's perfectly acceptable to say, we don't know yet, but we're working on it. In fact, that's often the most honest and scientific response. Here's something that I find particularly fascinating about this whole situation: the letters that Avi Lowe has been receiving.
He shared several of them in a recent blog post, and they're revealing, not about 3IATLAS, but about how this story is resonating with people around the world. A teacher from Italy wrote to thank him for his passion and transparency. A content creator from South Africa offered to help raise awareness. A visual artist from Kenya expressed gratitude for enlightening humanity. People from Mexico, the UK, Florida, everyone reaching out to say the same thing. Thank you for asking questions. Thank you for not settling for easy answers. Thank you for treating this seriously. That response tells you something important. People are hungry for this kind of science. Not dumbed down, not sensationalized, but rigorous and honest and open to possibilities. They want to be part of the conversation. They want to understand what's happening in our universe, even when, especially when, what's happening is uncertain and strange. And that's exactly the kind of engagement we need, because the questions raised by 3IATLAS aren't just scientific questions, they're philosophical questions. Questions about our place in the universe. Questions about what we should expect to find as we explore beyond our planetary home. Something changed. Just days after 3IATLAS completed its closest approach to the Sun, astronomers detected something they weren't expecting. What they saw was truly unexpected, a complex jet structure emanating from the object in multiple directions. This was not the simple tail you would expect from a typical comet, but rather something far more intricate. The fact that this phenomenon appeared just days after the object's perihelion, the point in its orbit when it was closest to the Sun, and its unexpected timing is what makes this discovery so remarkable. Let me ask you this. When was the last time you saw a comet behave like this? One that accelerated without any visible cause? One that changed color from red to deep blue in just a matter of days? One that lost its tail only to develop multiple jets pointing in various directions? If you're struggling to recall, that's because nothing like this has ever happened before. At least, nothing like it has ever been observed in any comet we've studied. Here's what we know now. And trust me, this is where things get truly fascinating. On October 24th, the Meerkat radio telescope in South Africa picked up something incredible: the first radio signal from 3IATLAS. But it wasn't a transmission like we might expect from a spacecraft or an alien signal. No, this was something different. It was absorption lines of hydroxyl radicals, OH molecules, being released from the object. This detection came just days after the object's perihelion, the point in its orbit when it was closest to the Sun. What makes this discovery so significant isn't simply that they detected it, but rather what the signal reveals about what's happening on the surface of this object. The hydroxyl radicals were detected at two very specific radio frequencies: 665 gigahertz and 1.667 gigahertz. These frequencies are crucial because they provided astronomers with essential data. The Doppler shift of these signals revealed something very interesting. The object was moving at exactly the velocity they had predicted. But here's the twist. Previous attempts to detect these same signals in late September failed. The radio silence was deafening. There was nothing. No signals, no evidence of absorption lines. Then, just as 3IATLAS swung around the Sun, these molecules appeared. It was as if the object had suddenly turned on. Before jumping to conclusions, it's important to understand what hydroxyl radicals are. These molecules are fragments of water molecules, broken apart by the intense radiation from the sun. Every comet releases them when it gets close to the sun. This is completely normal and expected behavior from any comet as it heats up. But the timing here is what is truly intriguing. The sudden appearance of these radicals after weeks of silence raises more questions than it answers. Was the surface of 3I-ATLAS so cold and inactive during its approach that it only began releasing gases at the very last moment before perihelion? Or is there something more complex happening? Could the surface be hiding something, an internal mechanism or an unknown process that suddenly activated when it reached the right point in its orbit? Professor Abby Lowe, a Harvard astrophysicist who has been studying 3I-ATLAS from the start, noticed something even more peculiar in his analysis. The thermal broadening of the O absorption lines matched exactly what you would expect from a surface temperature of approximately 230 Kelvin. This is incredibly cold, very, very cold. But what caught his attention even more was the width of those absorption lines. The full width at half maximum, a term astronomers use to describe the sharpness of absorption lines, was remarkably narrow, less than 1.12 kilometers per second. This suggests that the gases weren't being violently ejected into space. Instead, they were gradually and methodically seeping out of the surface. This slow release of gas in such a narrow bandwidth is unusual for a comet, which would typically show much broader absorption lines if it were releasing gases in an explosive fashion. But that's not the strangest part. What happened after perihelion is what truly has astronomers puzzled. The Atacama Large Millimeter Array, ALMA, one of the most powerful radio telescope networks on Earth, observed 3I-ATLAS and found something completely unexpected. The object was 4 arcseconds off its predicted trajectory. Now you might be wondering, what does 4 arcseconds even mean? Well, in astronomical terms, it's a lot. 4 arcseconds when you're tracking an object millions of kilometers away using precise instruments is significant. This is no minor measurement error. This is a real deviation from the predicted path. And what's even more intriguing is that the deviation wasn't random.
It was consistent with a non-gravitational acceleration. Something had nudged 3I-ATLAS off course. But what? Typically, comets experience such changes in direction due to outgassing, the release of gases from the surface as they heat up. As ice vaporizes, it creates tiny jets that act like miniature rocket engines, pushing the comet in different directions. This phenomenon is called outgassing, and it's completely natural. But here's the problem. The amount of acceleration observed in 3I-ATLAS was far too strong for an object that showed very little visible outgassing activity. If 3I-ATLAS had been releasing enough gas to push itself this far off its trajectory, we should have seen a massive coma, a cloud of gas and dust surrounding it. It should have been an active, brightly visible comet with a long tail, just like any other comet we've observed in the past. But instead, what did we see? A relatively subdued object that actually lost its tail shortly after perihelion. So, if it wasn't outgassing, what was causing this acceleration? Loeb proposed something that raised eyebrows across the world. He didn't completely rule out the possibility, however remote, that the acceleration could be the result of something artificial, perhaps an internal propulsion system. Now, before you dismiss this as science fiction, hear me out. Loeb wasn't claiming that aliens were behind it. He simply suggested that if no massive gas cloud was observed around 3I-ATLAS in the coming weeks, then the non-gravitational acceleration might, just might, be regarded as a technological signature. It's the scientific method at work. You observe something unusual, you try to find natural explanations, and when those explanations fail to fit,
you begin to consider alternative hypotheses. But let's delve deeper into what happened next, because this is where the mystery only gets more complex. Images from the Hubble Space Telescope and ground-based observatories revealed something truly remarkable. After perihelion, 3IATLAS began exhibiting a complex jet structure, not just a single tail streaming behind it, like the usual comet. Instead, multiple jets were emanating from various points on the surface, pointing in different directions. This was nothing like the typical behavior we see from comets. It looked less like a comet and more like something that was actively regulating its own trajectory. One of the most intriguing images came from the 2-meter twin telescope, which captured an image showing a sunward jet, material actively streaming directly toward the sun. This is highly unusual. Typically, comet tails are blown away from the sun by solar wind and radiation pressure. They stream behind the comet like a flag, fluttering in the breeze, always moving away from the sun.
But a sunward jet suggests something else entirely, material being ejected from the night side of the object, the side that's facing away from the sun, with enough force to curve around and point toward the sun. Now, here's where it gets really speculative. It could suggest directional venting from specific areas of the surface, where gases are actively being released. Why does this matter? If outgassing were purely passive, simply driven by the sun's heat, you'd expect the jets to be symmetrical, primarily concentrated on the sun-facing side of the object. However, the fact that jets were emanating from multiple locations, including the night side, suggests something much more complex. Perhaps the interior of 3IATLAS is maintaining heat even on the side that is not facing the sun. Or there may be specific vents or areas where gas is being released in a controlled manner. And then there's the bizarre color change. This is another mystery that needs to be addressed. Initially, when 3IATLAS was first observed in July, it appeared reddish. This is typical for objects in space. Cosmic dust and organic compounds tend to give objects a reddish hue. However, as 3IATLAS approached the sun, something strange happened. It began to turn blue, deep blue. By the time it reached perihelion, the object had shifted to a striking blue-green color, one that astronomers had rarely, if ever, seen in a comet. Now, there are natural explanations for color changes in comets. As a comet heats up, different types of ices sublimate at different temperatures. Water ice, carbon monoxide ice, and carbon dioxide ice, for example, vaporize at varying temperatures and can scatter light differently. However, the shift from red to blue is counterintuitive. Typically, as comets release dust, the particles scatter light, causing the comet to appear redder, not bluer. So what could cause this change to blue? One possibility is that we're seeing light scattered by very small particles, smaller than typical comet dust. When particles are exceedingly tiny, they scatter blue light more efficiently than red light. It's the same phenomenon responsible for why the sky appears blue. But if that's the case, where are these tiny particles coming from? Why did they only become visible as the object approached the sun? Another potential explanation, which ventures further into the speculative realm, is that we could be seeing emission from specific gases, such as cyanogen and diatomic carbon. These gases can produce a blue-green glow when exposed to sunlight. But again, why now? Why did these gases suddenly appear in such quantities during and after perihelion? The color shift raises more questions than it answers, and scientists are scrambling to find the right explanation. NASA quickly responded to concerns, trying to reassure the public.
Acting Administrator Sean Duffy addressed questions, including one from Kim Kardashian. Yes, that Kim Kardashian, assuring everyone that 3IATLAS was just the third interstellar comet to pass through our solar system. No aliens, no threat, just a comet doing comet things, he stated. However, not everyone is convinced that we're getting the full story. Dr. Brian Cox, a renowned physicist, publicly criticized NASA for what he called unnecessary secrecy surrounding 3IATLAS. In a pointed statement, Cox argued that NASA had been withholding crucial data from the public, especially the high-resolution images taken by the Mars Reconnaissance Orbiter on October 2nd and 3rd, when 3IATLAS passed within approximately 30 million kilometers of Mars. Cox didn't stop there. He pointed to the object's estimated age of about 7 billion years, significantly older than our solar system, and its unusually high nickel content, which suggested the object was composed of materials much older and tougher than anything typically found in our local cosmic neighborhood. And most provocatively, Cox mentioned that while an extraterrestrial origin for 3IATLAS remains highly unlikely, respected scientists such as Avi Lowe had not ruled out the possibility. Cox's primary concern wasn't about aliens, it was about transparency. As he put it, unnecessary secrecy only fuels conspiracy theories. When data is withheld from the public, when images are delayed or not released at all, it raises questions. What is there to hide? If 3IATLAS is just another comet, why not release all the data and settle the matter? This simple question, why, has now reached Congress. Florida Congresswoman Anna Paulina Luna formally requested that NASA release all data related to 3IATLAS, particularly the images taken by the Mars Reconnaissance Orbiter's HiRISE camera on October 2nd and 3rd when 3IATLAS passed within approximately 30 million kilometers of Mars. But Luna didn't stop there. She also requested supplementary data from the Mars Orbiter, the Perseverance rover, and other Mars missions that might have detected unusual activity near Mars after October 3rd when 3IATLAS passed the planet. Why Mars? Because the close approach provided an ideal opportunity. Mars-based instruments could observe 3IATLAS from an angle that Earth-based telescopes couldn't access. If there was anything unusual about the object's trajectory or surface activity, Mars missions would have been well positioned to detect it. The fact that this data hasn't been released yet has sparked even more questions. Is NASA being cautious, carefully analyzing the data before making it public? Or is there something hidden in those images that requires a more delicate approach? What we do know is that at the very least, the delay in releasing this data has fostered increasing skepticism.
The silence around 3IATLAS is not just an academic issue, it's become a public concern, one that has reached the halls of government. The frustration from scientists, along with the lack of transparency, has caused many to question whether the public is being kept in the dark about something significant. If NASA has the data, then why is it being held back? If 3IATLAS is just another comet, why not release all the images and put the rumors to rest once and for all? After all, transparency is a cornerstone of science, and without it, distrust grows. Despite the delays and controversies, the growing chorus of voices demanding more openness is a good sign. It shows that we, as a society, are not content to sit back and accept explanations without asking tough questions. We're willing to challenge the assumptions and make sure that the data we rely on is fully examined by all, not just a select few. Science, after all, is not just a pursuit for a few experts. It's a pursuit for all of us. And now, with 3IATLAS, we have a perfect opportunity to see how science works when everyone has a stake in the findings. One of the most pressing questions about 3IATLAS revolves around its unexpected trajectory. As mentioned, the deviation from the predicted path wasn't just a minor mistake, it was 4 arcseconds off. This kind of error in prediction doesn't happen often, especially when dealing with objects in deep space. But the deviation was consistent, and that means something is at play here, something that can't be easily explained by gravity alone. There is a growing consensus among some scientists that this could be a result of something more than just outgassing, a potential, unexplained force affecting its movement. The problem is that the observations don't match the expected model of cometary behavior. As we've seen, comets typically follow a predictable path, with their trajectories altered only by the outgassing of volatile materials. However, in this case, the object didn't exhibit the expected tail or coma around perihelion, which would be a clear indicator of outgassing. Yet it still experienced a strong deviation in its trajectory. And to make things even more perplexing, the amount of gas required to explain the acceleration doesn't match the observed visible activity. Where is all the gas? What could be causing this deviation if it's not the typical comet outgassing? This leads to the next fascinating theory. Could the acceleration be due to some sort of artificial propulsion system? While this idea initially seems far-fetched, it's not entirely out of the realm of possibility. As we've seen, the behavior of 3IATLAS doesn't fully align with natural comet characteristics. It's possible that we're dealing with an object that has been engineered for a long journey across the cosmos.
One idea that has emerged is that 3IATLAS could be a probe sent intentionally on an interstellar journey, perhaps even by an advanced civilization. This doesn't mean the object is definitely artificial, but the idea shouldn't be dismissed out of hand. As scientists, we have to remain open to all possibilities, no matter how strange they might seem. But for now, these are just hypotheses, speculative ideas that require more evidence before we can draw any conclusions. So far, there are no definitive answers. What we need are more observations, more data, more research. We need to observe 3IATLAS closely as it continues on its path through our solar system. The upcoming flyby on December 19th will be critical. We'll be able to see it at a much closer range, and we may get answers to some of the questions that have been raised. This is the moment to gather as much information as possible. Amateur astronomers, too, have an important role to play in this investigation. For the first time, we have an object from another star system passing through our neighborhood solar system, and it's visible to anyone with a decent telescope. If you're an amateur astronomer, this is your chance to make a real contribution to science. We may not have all the answers right now, but we're getting closer, and every observation counts. As we prepare for the December flyby, scientists around the world will be watching closely, examining the light curve of the object, tracking any changes in its behavior, and looking for anomalies that don't fit the typical comet model. But they're not alone in this. Thousands of independent observers will be monitoring 3IATLAS with their own telescopes, helping to fill in the gaps that the major space agencies might miss. In this sense, the data collection for 3IATLAS will truly be a collective effort, with contributions coming from both professional and amateur astronomers. But let's also consider the broader implications of this moment. If 3IATLAS is simply a comet, then its behavior is unprecedented, and our understanding of cometary activity will need to be revised. If, on the other hand, it's something more, something artificial, or something that challenges the limits of our current scientific understanding, then this could be a turning point. The discovery of 3IATLAS has already sparked significant interest in the possibility of detecting extraterrestrial technology, and as we continue to observe this object, we may be forced to reconsider our place in the universe. In the coming years, as our detection capabilities improve, we'll likely encounter more objects like 3IATLAS. Some will be boring, simple ice balls drifting through space, but others, perhaps, will show signs of something more, something that forces us to rethink what we know about the universe. 3IATLAS is just the beginning, and it's a reminder of how much we still don't know about the cosmos.
It's a signal that perhaps we're on the verge of discovering something that challenges the very nature of what we think is possible. So, as we wait for more data, as we continue to observe 3IATLAS in the coming weeks and months, let's keep our minds open. Let's continue asking the hard questions, and let's remain curious, because the universe, as it turns out, is full of mysteries waiting to be unraveled. This is an extraordinary time in science, one that may open the door to new discoveries and new understandings of the cosmos. As we continue to observe 3IATLAS, let's reflect on how this moment fits into the broader context of scientific discovery. It's not just about a comet passing through our solar system. It's about our ability to make sense of the unknown, to challenge the boundaries of our understanding, and to engage in critical thinking as a global community. For centuries, humanity has been looking up at the stars, wondering if we are truly alone in the universe. With the arrival of 3IATLAS, we are presented with a rare opportunity to confront that question in real time. The significance of this moment cannot be overstated. It's not just a comet, and it's certainly not just a passing curiosity. 3IATLAS is the third interstellar object we've detected passing through our solar system, and each one has provided us with insights into a universe much older, much more complex, and much more mysterious than we ever imagined. With every new interstellar visitor, we learn more about the nature of our cosmic neighborhood, and we begin to piece together a picture of the forces that shape our universe. The arrival of these interstellar objects forces us to re-examine everything we thought we knew about our place in the cosmos. They make us ask the big questions. How common are objects like this? What does their presence in our solar system tell us about the wider galaxy? How many other star systems have objects like 3IATLAS? Objects that may carry secrets about the origins of life, the processes that govern planetary formation, and the potential for other forms of intelligence. And while the presence of 3IATLAS might be unsettling for some, it's also a reminder of how much there is still to learn. The data we gather from this encounter could reveal not just new scientific facts, but new ways of thinking about the universe itself. If 3IATLAS truly is an artificial object, or if it behaves in ways that challenge the natural explanations we currently have, it could push us to rethink the nature of technological development, not just on Earth, but in the universe. Could this be evidence of an ancient civilization? Could we, one day, find other objects like this in our cosmic neighborhood? Or could the behaviors of 3IATLAS simply be the result of natural phenomena we haven't yet fully understood?
As we continue our observations, we must keep in mind that we are on the cutting edge of a new frontier in space exploration. The tools we have at our disposal are growing more powerful by the day, and the techniques we use to study interstellar objects are becoming more refined. The unprecedented nature of 3IATLAS means that we are breaking new ground in our understanding of the universe, and the knowledge we gain from this encounter will likely shape the course of scientific research for years to come. In the coming months, as we observe 3IATLAS pass closest to Earth, we will be given a rare chance to study an object that has traveled across the vastness of space from another star system. The data we gather during this flyby could answer some of the questions we've been asking for centuries, questions about the origins of life, the possibility of other civilizations, and the very nature of the universe itself. And as we observe this object, we'll be reminded that space exploration is not just about sending probes and satellites into the unknown. It's about uncovering the secrets of the cosmos and confronting the most profound questions about existence. As we await the December flyby, one thing is certain. 3IATLAS, whether it's a comet or something else entirely, has captured the imagination of people all over the world. It sparked a new conversation about the nature of space, technology, and life beyond our planet. This is not just a moment in the history of astronomy. It's a turning point in the way we think about the universe in our place within it. And in the years to come, as we look back on this encounter, we may find that the questions 3IATLAS has raised will continue to haunt us. Whether the object is truly an alien artifact or just an unusual comet, it has already changed the way we look at the universe. It has reminded us that there is still so much we don't know, and it has rekindled our curiosity about the stars and what lies beyond our small corner of the universe. Looking ahead, the questions that 3IATLAS has raised will continue to shape the future of astronomy and our understanding of interstellar objects. The more we study, the more we realize how much we don't know, how much remains hidden in the vast expanse of space. 3IATLAS has provided us with a window into the unknown, one that we are only beginning to peer through. And in the coming years, as we encounter more interstellar objects, we'll have the opportunity to refine our methods, enhance our technologies, and deepen our understanding of the cosmos. The real significance of 3IATLAS lies not in the answers we have, but in the questions it has inspired. These questions go beyond the scientific. They touch on philosophical, existential, and even cultural matters. What is our place in the universe? Are we truly alone, or are we just beginning to understand the cosmic community we are a part of?
These are questions that reach into the very heart of human curiosity, the drive to explore, to understand, and to seek out the unknown. And that's what makes the study of 3IATLAS so exciting. It's not just about finding answers. It's about embracing the journey of discovery, wherever it may lead. As we await its closest approach to Earth in December, there's a palpable sense of anticipation. For scientists, this is an opportunity to test the theories and ideas that have been forming over the past few months. For the public, it's a chance to witness history in the making. The flyby will be a key moment in our study of interstellar visitors, and the data gathered from this event could change the way we think about space and the objects that pass through it. Will 3IATLAS behave like a typical comet, with a predictable trajectory and a clear pattern of activity? Or will it continue to defy expectations and present us with even more anomalies that challenge our understanding of the laws of nature? The opportunity to observe 3IATLAS up close is a rare one, and it's one that we shouldn't take for granted. It's a moment that reminds us of the vastness of the universe and the mysteries that still lie beyond our reach. Whether or not we discover something truly extraordinary, the process of studying this object is itself a remarkable achievement. It shows how far we've come in our ability to observe and analyze the universe, and how much more we have yet to learn. As this journey continues, we must remember that it's not just the professional astronomers who play a role in uncovering the secrets of objects like 3IATLAS. Everyone can be part of this story. Whether you're an amateur astronomer, a student of science, or just someone with an interest in the stars, you can contribute to the larger narrative of discovery. The data we gather in the coming weeks and months will be analyzed, scrutinized, and interpreted by countless individuals around the world. This is the beauty of modern science. It's a collaborative effort, a shared pursuit that transcends borders and backgrounds. 3IATLAS is a reminder that we are part of something much larger than ourselves. It's a symbol of the boundless curiosity that drives us to explore, to understand, and to connect with the universe. As we look up at the sky, we are reminded of the incredible complexity of the cosmos and the infinite possibilities that await us. The discovery of 3IATLAS is not an end, but rather a new beginning, a stepping stone on the path to unraveling the mysteries of interstellar space. In the end, whether 3IATLAS is a comet, an artificial object, or something else entirely, the journey it has sparked will leave an indelible mark on the history of science. It has shown us that there's still so much to discover, and that the universe, in all its vastness, is far from fully understood.
As we continue to explore the stars, we will undoubtedly encounter more objects like 3IATLAS. Objects that challenge our understanding of the universe and force us to expand our knowledge beyond what we thought was possible. So, as we move forward, let's keep asking the big questions. Let's remain open to the unknown and embrace the curiosity that drives us. And when the time comes to look back on the story of 3IATLAS, we'll remember it as the moment when our perception of the universe shifted, when we learned to ask the right questions, and when we began to see the universe not as something distant and unreachable, but as something that is and always has been right in front of us. The implications of 3IATLAS extend far beyond the realm of science. This event has ignited the imagination of millions, pushing the boundaries of human curiosity and inviting people from all walks of life to engage with the cosmos in a way that was once unimaginable. The object's unexpected behavior, coupled with its origins from interstellar space, challenges the very fabric of our understanding of the universe. It forces us to reconsider not just the science of space, but our place within it. As we look toward the future, the discoveries made through the study of 3IATLAS will undoubtedly shape the way we approach the study of other interstellar visitors. We're entering an era where the lines between science fiction and scientific exploration are becoming increasingly blurred. The idea of exploring objects from beyond our solar system was once relegated to the realm of imagination, but now it's becoming a tangible reality. This is an exciting time for both professional astronomers and the public alike, as we witness the unfolding of a new chapter in the exploration of space. In the years to come, we will likely see more objects like 3IATLAS. As our technology improves, our ability to detect and study interstellar objects will continue to grow. And who knows what other mysteries we will uncover. Each new discovery brings with it a multitude of possibilities, expanding the horizons of what we know about the universe. With each interstellar visitor, we have the chance to learn something new about the nature of the objects themselves, about the processes that govern their movements, and perhaps even about the origins of life in the cosmos. The key to unlocking these mysteries lies in collaboration. The scientific community is built on the exchange of ideas, the sharing of data, and the collective pursuit of knowledge. By working together, we can solve the puzzles presented by objects like 3IATLAS. Whether it's professional astronomers using the most advanced telescopes and instruments, or amateur astronomers contributing valuable observations from their backyards, everyone plays a part in this grand endeavor. The more data we gather, the clearer the picture will become. But it's not just about the data.
It's about the questions we ask and the way we approach the unknown. The story of 3IATLAS has taught us that science is not just about finding answers. It's about embracing the mystery. It's about being open to the unexpected and being willing to question everything we think we know. As we continue to observe 3IATLAS and its behavior, we must remain flexible in our thinking, ready to adapt and evolve our theories as new evidence comes to light. Moreover, the cultural impact of 3IATLAS cannot be understated. The excitement surrounding this object has captured the public's imagination, sparking discussions about space, extraterrestrial life, and the future of human exploration. The possibility that this object could be something more than a comet has sparked debates about the nature of intelligent life and what we might encounter beyond our planet. These discussions are not just confined to the scientific community. They are being had in classrooms, living rooms, and online forums around the world. This is the power of discovery, the way it can unite people in curiosity and wonder, pushing the boundaries of human thought. And as we continue this journey, we must keep in mind the importance of scientific literacy. The more people understand the science behind these discoveries, the more equipped they will be to engage with the bigger questions about our universe. The story of 3IATLAS is just one chapter in the ongoing exploration of space, but it serves as a reminder that the more we learn, the more we realize
how much we still have to discover. We are at the beginning of an exciting new era in the study of interstellar objects, and the questions raised by 3IATLAS will continue to fuel our quest for knowledge for years to come. In conclusion, whether 3IATLAS is a comet, an artificial object, or something entirely unexpected, it has already accomplished something extraordinary. It has reignited our curiosity about the cosmos and reminded us that the universe is full of mysteries waiting to be solved. The questions raised by 3IATLAS have opened up new avenues of inquiry, pushing us to think beyond the traditional boundaries of space science. And while we may not have all the answers yet, one thing is certain: this object has changed the way we look at the universe, and in doing so, it has changed the way we think about ourselves. As the days go by and we continue to study 3IATLAS, let's remember that the pursuit of knowledge is a never-ending journey. We may not know what lies ahead, but the excitement of discovery, the thrill of unraveling the unknown, is what drives us forward. The future of space exploration is bright, and 3IATLAS is just the beginning of what promises to be an extraordinary era in our understanding of the cosmos. As we move forward, the significance of 3IATLAS will continue to unfold in unexpected ways.
The knowledge we gain from studying this interstellar object will have ripple effects on the broader field of astronomy. The methods developed to track, study, and analyze such objects will set the stage for future missions and investigations of interstellar space. We might not have answers to all the questions yet, but the tools and techniques we're developing today will lay the groundwork for discoveries we can't yet predict. In the next few years, as the focus on 3IATLAS wanes, the lessons learned from its study will fuel new scientific inquiries. We will undoubtedly discover more interstellar objects like it, and the experience we gain in analyzing this first visitor will be invaluable. With better technologies and more advanced instruments, our ability to observe and understand these objects will improve exponentially. We will refine our techniques for measuring the behavior of objects far beyond our solar system, and, in doing so, we may uncover entirely new phenomena that challenge even the most advanced models of astrophysics. The study of interstellar objects like 3IATLAS is likely to become a burgeoning field of research. Imagine a future where interstellar probes and telescopes designed to study distant star systems are commonplace, and humanity has a comprehensive understanding of objects that travel between stars. This could radically transform our understanding of the cosmos and our place within it. What if we could identify patterns in the trajectories of interstellar objects, or detect clues about the formation of stars and planets in far-off systems? These are the kinds of breakthroughs that could come from continued study of objects like 3IATLAS. On a broader scale, the study of interstellar visitors pushes the boundaries of how we view our universe. For decades, astronomers have been focused primarily on objects within our own solar system. But the discovery of Oumuamua and 3IATLAS is opening our eyes to the wider, more mysterious universe that exists beyond the gravitational pull of our Sun. These objects serve as messengers from far-off star systems, bringing with them knowledge that has traveled across the vast distances of interstellar space. They are not just cosmic debris. They are windows into other worlds, other civilizations, other histories. If 3IATLAS continues to defy expectations, if it continues to exhibit behavior that can't easily be explained by natural processes, then we may be on the verge of discovering something much more profound. Could there be more interstellar objects out there with unusual properties waiting to be discovered? What secrets do they hold about the origins of life and the nature of the universe?
How do they challenge our understanding of physics, chemistry, and even the possibility of intelligent life? While we cannot jump to conclusions about the true nature of 3IATLAS, we should be prepared to embrace the unknown.
If this object turns out to be entirely natural, we will have gained invaluable knowledge about the forces that govern space. If, on the other hand, it reveals something more exotic, something artificial, something created by a distant civilization, then we will have opened an entirely new chapter in the story of human discovery. Either way, we are at the threshold of an exciting new era in our understanding of the universe. In many ways, the questions raised by 3IATLAS are questions that humanity has been asking for millennia. Are we alone in the universe? What lies beyond the stars? How did life begin? And perhaps most importantly, what does it mean to be human in a universe that is so vast, so mysterious, and so full of unknowns? As we continue to observe 3IATLAS, it's essential to remember that the pursuit of knowledge is not just about finding answers. It's about asking the right questions. It's about the curiosity that drives us to look beyond our planet and explore the cosmos. Whether we are looking at distant stars, interstellar objects, or the possibilities of life beyond Earth, we are part of a larger story, one that transcends the confines of our small world and connects us to the broader universe. And so, as we move toward the December flyby and beyond, let us remain vigilant, curious, and open-minded. The journey of discovery is never over, and the universe is always full of surprises. 3IATLAS is just the beginning, a signal from the stars that we are not alone in our quest to understand the cosmos. And as we continue to look up, we will undoubtedly encounter more questions, more mysteries, and more wonders waiting to be uncovered. The universe has much to reveal, and we are just beginning to scratch the surface.